Hello and welcome to this recorded e-learning about FPGA power management design techniques. My name is Frank Nelson. I'm a Xilinx technical trainer and course developer. I'll be your instructor for this module. After completing this module, you'll be able to explain why you should target as much of the dedicated hard IP as possible, describe how your design's power consumption is dependent on your use of control signals, explain how some common design techniques can improve your design's power consumption, and use the newest architecture features to improve your design's power consumption. To reduce your FPGA's power, you have to look for opportunities to reduce the logic in your design. This will allow you to use as small a device as possible and save more static power. You'll also need to use as much of the dedicated hardware resources, such as the DSP slices and block RAM resources, as available. These resources use less power than an equivalent function built with CLB logic. To do this, you'll need to be comfortable using the core generator and instantiating components from either the Xilinx Unified library or with the core generator. As you'll see in a couple of slides, you will also need to manage your control signal usage. You will also need to be comfortable using your synthesis tool to infer the optimum resources, and this will require you to be able to verify which resources are used by using your synthesis tool schematic viewer. You should remember that using the dedicated hard IP blocks is one of the most powerful ways to lower both your static and dynamic power consumption. They lower static power because total transistor count is lower in the dedicated hardware than it is when building an equivalent component using CLB logic. These design practices are some of the most useful for reducing the size of your design. Time slicing allows a circuit to perform less work and use less power. Anytime you can time slice your application, the more power you'll end up saving in the application. You should also consider using alternative design practices to target unique and common components to extra dedicated hardware resources. In this example, one of the most useful is migrating a required finite state machine to a block RAM. These design practices may take a little extra effort to optimize the component and then instantiate it into your FPGA, but they are very useful at allowing the user to get the most out of the dedicated hardware and then pack more logic into the FPGA and reduce their overall power consumption. One of the side benefits to reducing the number of LUTs and flip-flops to your design use is that it also allows you to improve design speed. You also need to be aware that over-constraining your design during synthesis encourages the synthesis tool to replicate logic automatically. Designers also need to take special care when they are migrating an existing design to a newer product because the newer products have a more efficient 6-input LUT, and the older devices had a 4-input LUT. Now this is important because many FPGA designers have used pipelining to optimize the speed of a data path. If an older design was pipelined, it probably has several unnecessary flip-flops that will actually limit the performance and increase the power necessary if it's targeted to a newer device. These designs should be re-pipelined appropriately for the architecture. Remember that when you instantiate a primitive, the port functionality you instantiate is what you're going to get. So if you instantiate a register, or a core that uses a register, make certain that the behavior of the flip-flop is what you want and that you understand the caveats associated with the use of that flip-flop's control signals. It is important that you understand that the FPGA architecture also dictates what types of control signals can be used. For example, a block RAM has a synchronous output register. If you try to infer an asynchronous output, your synthesis tool will not infer that output register. This can affect your device utilization and output performance of that block RAM. Your synthesis tool can also infer a high fan-out control signal, so be sure to evaluate what you're getting with your synthesis tool schematic viewer. Active low signals use more LUTs because they require inversion before they can directly derive the control port of a flip-flop. This inversion must be done with the LUT and thus takes up a LUT input. Likewise, because only a single reset can be brought to the register, if the remaining logic to be grouped does not share all common control signals, it cannot be grouped into the same slice. If you use any hierarchical design techniques, meaning you are using partitions or maintaining hierarchy, instantiating cores, using multiple netlists, and then using bottom-up synthesis, be aware that it can increase the number of control signals in your design because the flip-flops do not have a programmable inverter. With hierarchical design practices, each signal would have a different name, and you would still have to run each signal through an inverter, which means you're burning a LUT input or even a whole LUT. This example shows that when you use hierarchical design methodologies, the synthesis tools and the implementation tools cannot merge this logic into the same slice. This is because the designer is not allowing optimization across a hierarchical boundary. This would not happen if the designer had planned on sharing control signals across the design and designed appropriately. Suggestions for faster and smaller designs include using synchronous set and resets whenever possible, using active high clock enable and set and reset signals. Note, no local inverter for those secondary control signals exists. Trying to build your design with as few control signals as possible. And then some other rules to recognize is clocks and asynchronous sets and resets always connect to the control port of the flip-flop. Asynchronous sets and resets will have priority access to the control ports over synchronous sets and resets. And finally, clock enables and synchronous sets and resets can become control signals to your system. Be careful when you are migrating designs to a different architecture or merging designs into one device. In this case, the design had an embedded DCM and a lower level block, and if the designer did not evaluate their design, they would now have two instances of the same block. In every design, the DCM and PLL power consumption is considerable, so this can really add up. So pull those DCMs and PLLs out of the top level of your design hierarchy so they are not replicated by your synthesis tool. You should also take full advantage of the BuffG mux, BuffG clock enable, and the BuffH clock enable to gate an entire clock domain for power reduction. Now this can be done to pause the clock in an entire clock region if you'd like. Likewise, for applications that only pause the clock on small areas of the design, use the clock enable pin of the FPGA register for that functionality. In summary, to reduce your design size, consider targeting the dedicated IP as much as possible. Do not overconstrain your design during synthesis. Remove any unnecessary pipeline stages if you're migrating the design. Minimize your design's control signal usage. Understand the control signals needed by your cores and then share them through your design if you can to minimize the number of control signals your design has. Use active high control signals. Use synchronous sets and resets. Minimize the use of DLMs, DCMs, or PLLs in lower power applications. And use the BuffG mux, BuffG clock enable, and BuffH clock enable primitives to reduce the unnecessary toggling and dynamic power consumption of your design. Well, there are lots of places to learn more about FPGA power consumption, and they all start at support.xilinx.com, but we do want to mention a couple of things that are very useful to you. The Spartan 6 FPGA Power Management User Guide, UG394, is very helpful to understand some of the power management features that are included in the Virtex 6 and Spartan 6 devices. So note, there is not an equivalent document for Virtex 6. Check this one out, though. Also, be aware of power consumption in the new 65nm FPGAs by reviewing the white paper 246. I think you'll find both of those very helpful. If you would like to see what other courses we offer or what other free RELs are available to you, go to the Xilinx Education link you see here. In particular, we want to direct you to the Designing with Spartan 6 and Virtex 6 device features, which discusses all of those detailed architectures in more detail than we have time to do here. There's also a number of other RELs that discuss power management, including what are FPGA power management HDL coding techniques, as well as information that's specific about Spartan 6 and Virtex 6. But whatever you do, please take a second and let us know what you thought of this REL. Click on the icon at the top of the page and please tell us what you thought. Again, my name is Frank Nelson. You've been listening to the What Are Power Management Design Techniques REL. Thank you for listening and thanks for your business.